like it? So good. Okay, I'm happy. Thank you. Are you working on this? It's a nice field. It's many people now the theoretical stuff that we can do.
Last time we met was in Southampton, right?
Yeah.
So it was in Europe.
It's to show that the same issues. And so.
Awesome.
Shall I go?
Yeah.
Okay. Okay, welcome to the Simons Institute, everybody. My name is Sampath Kannan, and I want to say a few words about the Simons Institute before handing off to the organizer, Ginger. I hope at least one person here is coming to the Institute for the first time, and these remarks are meant for you. Great. A few people, that's wonderful. Well, the Simons Institute was founded in 2012 through a generous grant from the Simons Foundation, and their grant has sustained us for the last 10 years and for the next 10 years as well. And what the Institute does is pretty unique in computer science. There are a lot of these institutes in mathematics, but in computer science, I believe we are the only institute that brings together researchers for sustained collaborations over an entire semester. And we fund a whole number of fellows, as we call them, people right at the cusp of going from grad school to faculty positions and help launch their careers quite often. So our focus is on theoretical computer science, but we take a broad view of this and we look at what can be addressed in other fields using a lens of theory, lens of algorithms and complexity. And so we have been engaged in many different areas: physics, biology, social science, a variety of different areas like that, but closer to home also like electrical engineering and so on. But we are especially happy these days to try to find what theory has to say again about machine learning in a broad sense. After all, machine learning and theory were very close in the 80s. Pack learning was one of the foundations of machine learning. They kind of drifted apart, and maybe they're getting back together because they need each other. So we hope that this workshop will be one more in the line of workshops and programs we've held in trying to find the theoretical angle in machine learning more clearly. Anyway, have a great workshop. I will tune in from time to time online, and I look forward to your workshop. Thanks.
All right. Hi, everyone. I'm Ginger Smith. I'm a professor at CMU and one of the co-organizers of this workshop and of the program more generally. And I'm going to give a super brief, just some opening remarks, giving you some context for the workshop before we get started and hear from our first speaker, Peter. So I just wanted to point out that this is one of 3 workshops that we're having this semester. So we have 2 coming up, one on trust and decentralized systems, one on agency and collaborative learning, and we also held the boot camp here a few weeks ago. This workshop is co-organized by John Ducci, Anastasia Koloskava, Kshitij Patel, me, and Natty Srebro, and we're really excited to have you all here today. A really, really quick intro for motivation for this workshop is that more and more in the field of machine learning, data is not coming from just one single source, one large sort of monolithic underlying population, but from many sources. And the field of federated learning has really taken advantage of this fact. So one sort of distinct thing about federated learning is that it views data coming from these clients as being generated from these individual sources, sources that have control over their data, sources where these data sources might differ, where these clients have agency in this process. They might have different risk portfolios, for example. So all of these things are things that we can actually model in the system in federated learning. But this is also, I think, indication of a bigger picture here around collaborative learning in the field of machine learning, which is that more and more frequently when we're building models in the context of machine learning, we're learning from multiple sources and possibly stakeholders. So we need to think about things like how do we incentivize people to participate in this process? How do we develop schemes that are trustworthy? And how do we effectively model these heterogeneous sources? Okay, so what are some of the questions we might be answering in this workshop? We're thinking about things like how can we sort of define the goals of federated and collaborative learning? How should we be modeling these heterogeneous sources? Can we actually characterize these notions of heterogeneity? And can we understand the performance of various methods, for example, efficient federated optimization methods, in light of these underlying assumptions around heterogeneity? So, you might see things like how do we formalize definitions of heterogeneity, formalize the goals here, understand things like local training in light of heterogeneity or communication compression. How can we characterize additional forms of heterogeneity? So we've seen a lot about data heterogeneity. There might also be other forms of heterogeneity, like systems heterogeneity, that come into play. And heterogeneity, if you think about, for example, scraping all of the data from the internet, there's a lot of heterogeneity in this data. Data is injected now that we're thinking about building these massive pre-trained models at various parts of this pipeline, both in pre-training but also in adaptation. There's a bunch of sources of data, a lot of heterogeneity there. So how does this change some of our understanding of these areas? Okay, in terms of the workshop agenda, so we have, every day of the workshop, we're going to have a really exciting set of talks. I wanted to also point out a few other activities that are happening throughout the week. So today we'll have a reception from 4 to 5, so please stick around. There'll be some light snacks, and we'd love to see you there. On Tuesday, so today is a little more optimization focused. Tuesday, we'll have a little bit more of a focus on privacy. And we'll also have a talk from Brendan McMahon, who has led a FL team at Google for some time. This will be the RMK lecture. Please make sure to attend this talk. It's going to be really great. On Wednesday, we have, again, a nice set of talks, thinking a little bit more broadly about heterogeneity, both in terms of optimization, but also modeling and other aspects of the ML pipeline. We will also be having a group hike that evening. So please stick around for that. On Thursday, we actually have 2 really interesting activities sponsored by Jane Street. So one is an estimathon. Has anyone been to one of these before? I think the rough idea is that you'll be looking at some actual estimation sort of problems together, and there's a sort of contest, and there's snacks, and it's going to be a really fun event. So if you're interested in this, you have to register beforehand. So please make sure to do that. And there will also be an AMA from Jane Street later that evening from 6 to 8, also here in Simons. All right, and on Friday, we have this final sort of activity that's deviating from the normal schedule of talks, which is that we're going to have a group discussion around open problems in this space, sort of reflecting after the end of the workshop at the end of the week here. So please make sure to stick around for this. This will be an interesting discussion. All right, any questions before we go ahead and get started? Cool. All right, then I will pass things over to our first speaker. So we're very fortunate to have Peter Richtarik, who is a professor at KAUST here today. He gave a really excellent tutorial on federated optimization as part of the boot camp a few weeks ago. So if you're interested and want to get up to speed on that space, I would highly recommend that tutorial. And today he's going to be talking about a class of methods more broadly in optimization, looking at deep learning optimizers. So very important for the field of federated learning, but also machine learning more generally. So excited to hear from him. Do you need this? Oh, you got it.
I have this one. I need to connect this again. Okay, good. Good morning, everybody. Thanks for making it for the first talk. It's a great pleasure to be here again after a month. I've been here for the boot camp, and I talked a lot about heterogeneity, maybe too much. Those of you who were here, maybe you're already tired of that, so there's almost 4 hours of content. So because of this, I decided that today I'll speak about something slightly different, not entirely different, but most of my talk, if not all of it, will be about something different. It's very closely related to, of course, federated learning and collaborative training and so on, but maybe something a little bit forward-looking. So the title is From the Broximal Point Method to Efficient Training of LLMs. So the Broximal Point Method is something, I'll explain what it is if you haven't heard of it. How many of you have heard of this thing? Okay, something, yeah. So Sebastian attended workshop at KAUST where I gave this talk for the first time. So it's something that is completely useless, but mathematically beautiful. Okay, so it's an amazing mathematical framework of thinking about optimization, but you can't implement it, so it's useless. However, you can implement approximate versions of it, and then it becomes very useful, and you can train LLMs with this, and you get state-of-the-art performance. But then you have to really depart from the theoretical, from the beautiful theoretical framework to some approximations. So some of the content is joint work with these people from my lab. Mostly with Kaya Grundkowska, but also with these other people. And there are 4 parts to what I'm going to talk about, and I have no time to cover all of this. So, and worse than that, the stuff relevant to this workshop is really the part 4, which I won't really have time to get into. But I want to tell you, this is where it gets relevant to federated learning and collaborative training and so on. So once I cover all of this, I would then be ready to cover muon and compressed version of this, because you want to do maybe communication and compression, you want to do error feedback for these kinds of methods, but I won't be able to get quite there. Before that, so this is the federated setup. This is about the non-federated setup, single machine setup. And what I will really mostly talk about is all of this, which is preparation for these other parts. I think I'll have some time for the first 3 parts. The last one maybe if I really speed things up a lot. Okay, so Broximal Point Methods. So this is based on, my talk is based on these 2 papers. However, when we came up with this idea and posted the paper on arXiv on the same day, one student of mine who was not part of this collaboration and Aaron Sidford sent email to me and said, oh, we've seen something like this in some other papers. So in fact, we rediscovered something that was studied already by other people, but the intersection is not that large. So there's a different focus in these types of works. Okay, so to set, to come up with a setting here, with something concrete, we'll think of minimizing a single function f in d dimensions, and we will make very few assumptions about the function. So convexity is there, but think of these other properties as just some regularization properties. The function is proper, closed, and convex. Set of minimizers is non-empty, and you start with a point where the function value is not plus infinity. Now, why do I talk about the convex setup when, in fact, in deep learning, we work in the non-convex world? There are 2 reasons. One reason is I just want to tell you what would happen in the convex setup, because then the theory is very nice. It turns out that this theory extends to non-convex setup also, very, very naturally. And I have maybe 2 or 3 slides on this as well. So covering the convex setup already tells you a lot about what will happen in the non-convex setup. Plus, we know that current optimizers in deep learning are really optimizers designed for non-smooth convex optimization rather than non-convex optimization. So for some mysterious reason, optimizers designed for convex optimization are those that work best. So what is the Ball-Proximal or Broximal operator? So this is not proximal operator. This B is not a typo. This is Broximal operator. What is this? So for those of you who know what is proximal operator or proximity operator, which is this, you want to minimize function f, and you say, okay, I want to minimize, instead of f, quadratic perturbation of f. So the perturbation is you penalize quadratic distance from x. There's some parameter gamma here. So you have a penalty. So you want to minimize f, but you don't want to be too far from x. And as you play with gamma, if gamma is very tiny, you put a lot of weight on the penalty. So the output of this argmin, will be something very close to x, right? And if gamma is huge, then you kill this penalty, and the output of this will be minimizer of f. So the way I want you to think about this proximity operator, this is some sort of an interpolation between x, the starting point, and the argmin of f, some sort of a path. Imagine some sort of path controlled by gamma, okay? Now, what is the proximity operator? It's almost the same thing, but you turn the penalty into a hard constraint, okay? So what happens if t is 0? Well, then the output is just x because you're not allowed to move away from x. And if t is infinity, you're allowed to move arbitrarily far, so the output will be the minimizer of f. So this is a different way of parametrizing some kind of interpolation between x and argument of f. Okay, so looks very similar. And there is a method, very well-known method, the Broximal Point Method, which is based on iterating this proximity operator. The Broximal Point Method will be the analog of this by iterating the proximity operator. It turns out that they have different theory. The theory of iterating this operator is much stronger than the theory of iterating this operator. And somehow, approximate versions of this turn out to be related to Muon. In fact, the Muon algorithm, which is now replacing Adam and AdamW, can be thought of as some sort of a stochastic first-order approximation of whatever is going on here. Okay? So I want to cover the Broximal Point Method in its pure form first, so that we get some intuition into what's going on. Okay, so the bxt is just the ball-centered x of radius t. So I'll be using this notation. Okay, so in order to formalize assumptions, I'll use these two assumptions. The function is proper closed and convex, as mentioned before. And x is in the domain of f, which means function value is finite, not infinite, at x. And it turns out we have this first Brox theorem, which says that the proximity operator is non-empty under these assumptions. So something will be spit out of the operator. It doesn't have to be a singleton, but it's definitely non-empty. However, if the set of minimizers of f and this ball, if they intersect, then obviously the output will be something which minimizes f. Right? So the Brox might be multiple valued, set valued, but you must output something in argument of f. If the intersection is empty, so if the minimizer of f lies outside of this ball, then it turns out that the Brox is a singleton. And moreover, the distance between x and the Brox is going to be exactly t. So iterating Brox from x to Brox of x goes all the way to the boundary of the ball, and there's just a unique point to which this is going to jump. So you can base an algorithm based on iterating Brox under these assumptions because the algorithm is going to be well defined. It will always output just this singleton on the boundary. Okay, the second Brox theorem says something of this type. Okay, there's certain inequality. I don't want to get into this, but what I want you to appreciate is that if you're going to be proving convergence result for this Brox method, for this Broximal Point Method, this inequality is the first step in the proof. You start here and you continue. That's the point of this theorem. So we know the Broximal Point Method is, you choose some radii tks, could be fixed, you could vary them in any way you want, and you keep iterating this proximity operator. So let's look at some picture here. So here you have a function which is quadratically looking, but it's not exactly quadratic. I just cut off the bottom so that this orange ellipse is the set of minimizers of f. And I start from x0, and I choose some ball of some radius, and I chose it exactly in such a way that it touches the contour line of the function right here. And I ask the question, what is the minimizer of function f in this green ball? Obviously, it's going to be this point x1. So I move there. You can see here that the first Brox theorem, which says this is going to go to the boundary holds, and we have a unique point. Now we repeat. We iterate the Brox with the center x1. We go to x2, and so on and so forth. So now we choose larger radius for some reason. We go to this point x3. And at this point, the ball is large enough that it intersects with the orange argument of f. So we jump directly to one of those minimizers. So in this example, this Broximal Point Method, or BPM, solves the problem in exactly 4 iterations. So this is not a coincidence. There is a theorem, which I'll present later, which says that this method, for any proper closed convex function, is going to minimize f in finitely many iterations. So this is not an iterative method, it's a direct method of optimization. In fact, to the best of my knowledge, it's the first direct method of optimization. just finitely many steps. Okay, so now there are at least two alternative ways of thinking of the Broximal point method. First of all, if the function is convex and differentiable, then the Brox is normalized proximal point method. Okay, so if we didn't divide this gradient of f at xk plus 1 by its norm, this would be the proximal point method. But we do, so this is some sort of normalized proximal point method. Okay, so that's one interpretation. And second one relates to the Ball envelope. So just like you have more envelope of a function, you have the Ball envelope, which we introduce in the paper, and this just outputs the minimum of f on the ball centered at x of radius t. Now, imagine function x squared, that's the blue function. The Ball envelope with t is equal to 1 is going to be this red function, which is also just x squared, except at the 0, you just push it away to -1 and 1. You set everything 0 in the interval -1 to 1. So you have a function which looks similar, but it's not exactly the same function. And now you can ask the following question. What would happen if I applied gradient descent to this Ball envelope, to this red function? It turns out that's exactly the Broximal point method applied to the blue function. So somehow this red function encodes, it's future looking because it encodes information, local information about the behavior of f in a neighborhood of size t. Okay, so this is the formal statement. If the function is convex, L-smooth, and the next iterate is not going to be a minimizer of f, then one iteration of this Broximal point method is just normalized gradient descent applied to the Ball envelope. Okay? All right, so now let's look at some convergence results. So first of all, let's recall the assumptions, proper closed convex, and so on and so forth. I mentioned this before. I'll say something about the non-convex part a little bit. This is not covered in this talk. It's not true anymore because I included two slides on this. So first of all, obviously, and this is a very obvious result, if the set of minimizers and the ball intersect, then obviously in one step you solve the problem. Okay, so we've seen this on this picture, and that's the result. So you start here, the ball is large enough, so it includes the set of minimizers. Obviously this this Brox operator is so powerful that it just goes to the set of minimizers right away. Okay, so if the intersection is empty, you go to the boundary. So this observation is not just a coincidence, doesn't apply just to these quadratically looking functions, it applies to every proper closed convex function. You go to the boundary. So now a proper convergence result. So if this ball does not intersect the set of minimizers, you decrease the distance to a minimizer by at least the radius squared, however large the radius is set. And there's no assumption on how large this radius can be. You can think of it as some sort of a step size parameter, but unlike in gradient type methods where you have an upper bound on the step size, here in the theory you don't have any upper bound on how large the radius can be. So if you just rewrite this right-hand side into this form, which is completely equivalent, you will see that this is basically a hidden linear convergence result, right? Because you take the previous distance square and you multiply it by a factor between 0 and 1, so you get linear convergence rate. However, this linear convergence rate is very, very powerful because notice that even if you fix this radius, tk, to a constant, it's going to improve as you get closer to the solution. We know that the distance to the minimizer monotonically decreases because of this. So this denominator must be decreasing as well. So this linear rate must be improving. That's why we call it super accelerated linear rate. It accelerates at every step. It gets better and it converges to 0. Not only this is true, of course, if the radius is larger, you get faster convergence. And notice that this linear convergence rate does not depend at all on the conditioning of f. So f doesn't have to be differentiable, so it doesn't have to be L-smooth, doesn't have to be strongly convex. So there's no notion of something like L over mu condition number. And the function f doesn't appear at all in this rate except for the location of x star. So the condition number is just the location of x star, basically. That's the only way in which this rate depends on f. So this is one of the very nice things about this method, that it doesn't depend on condition number. Now, why does this matter? Because in optimization, in machine learning, we really care about coming up with algorithms which have reduced dependence on problem parameters, on smoothness constants, on strong convexity. We want to have some acceleration, momentum. Here, you don't need anything like this because you automatically get perfect behavior. Yes?
Slightly confused by why you call this linear convergence. If t is constant, if I'm close to the optimizer, that term just stops contracting, right?
Which term?
The contraction term.
So it keeps improving, right?
T is constant. If
T is constant.
If t is constant.
Well, this distance is upper bounded by x0 minus x star, right?
Right.
And that's why even if t is constant, this is some constant between 0 and 1. But it's better than that because this denominator, this distance, keeps shrinking. Why does it keep shrinking? Because of this, right? So it is a faster than linear rate. It's, in the worst case, it's going to be this 1 minus t squared divided by x0 minus x star squared. But it's going to get better and better precisely because of this inequality. Okay?
So
Yes?
here, you can just separate the two terms additively. So
Separate what two terms?
you have the analysis of xk minus x with a square norm,
Right?
and then you have minus tk as a
That's what this is. This is the same thing. Right? That's exactly what I'm saying. So this is the result, and I just choose to think of it this way in order to interpret it. That's all.
So the
This
analysis,
is completely the same thing.
the analysis is just on the shrinkage of the norm. Right?
Yeah, the analysis says this, that this happens. And I just choose to write this right-hand side in this form in order to interpret it as a linear convergence result or something faster than linear convergence result.
And if tk is too big, then,
That's all.
then how can this inequality hold?
Well, it cannot, but then this assumption is going to be violated, right? So if this ball does not intersect with a set of minimizers, then this is true. If it does, I solve it in one step. So that's what would be violated if because if tk is as big as this distance squared, this intersection is not going to be empty. But then you get, so this is basically the rate until the last step, and in the last step you just directly hit the set of minimizers. Okay? Any other questions? Okay. So there's that. Now, if these radii squared add up to at least the initial distance squared, then that kth iterate has to be a global solution. So for instance, if you fix the t, then you need x0 minus x star squared divided by t iterations, and then you hit the set of minimizers. So this is why it's direct method of optimization, just finitely many steps. Okay? Now, you can get a similar result to the distance result in terms of function values. So this is also a linear rate. It also improves with the distance and with the radius, but this expression is not 1 minus this, but 1 plus, but then you take inverse of that. This is basically the same thing. So this is also super accelerated linear rate. And again, what I want to stress here, we don't need the strong convexity at all. This is true for any convex function. We don't even need differentiability, and we don't need smoothness at all. We don't need finite valueness, proper closed convex. So this is stronger theory than for proximal point method, because for proximal point method, you need strong convexity, or strong convexity is sufficient for linear convergence. There's a textbook example. Now you have some more results. The gradient norms keep shrinking and so on and so forth, but I don't want to spend too much time on this. So what I want to show you is our motivation, how we actually came up with this algorithm. We're not interested in convex optimization. We're interested in non-convex optimization. We were thinking about this. And we had this kind of a picture in mind. So I believe Sebastian wrote a paper where he had a function like this, maybe exactly the same one. So this is a function which looks like absolute value of x plus some little strange wiggly oscillation. So if you zoom out, this looks like absolute value of x, but locally gradient method is going to be stuck in these local minimizers. And now, if you use any gradient type method, it will get stuck in one of these local minimizers, right? And we're asking the following question. How should we design an algorithm which is not going to be stuck in these local minimizers? And if you think of the ball of this Broximal Point Method with radius 2 pi, it will not get stuck because the radius is always large enough that it will jump from point here to the next better local minimum. It will be able to jump away from the local minima, and probably it can converge to global minimum from any starting point. But this is at the cost of the oracle being much, much stronger than the gradient oracle. You have to be able to minimize the function on a ball of sufficiently large radius. So this is not the result that is for free. Okay? So this is what we really have in mind. And that's how we think of the algorithm. Maybe we should be inspired by this method in order to design methods which can solve non-convex problems to global optima rather than to stationary points. But then we need to rethink the foundations of our algorithmic design. And in this paper, which is not on arXiv yet, but it's submitted, we show that this global convergence to global optimum holds for much larger class of functions than properly closed and convex. It holds for many non-convex functions, obviously not all, and in particular for star convex, quasi-convex, if aiming condition holds. Under all of these conditions, our condition, which we call proximal aligned functions, is satisfied. And under that condition, we get global convergence. OK. So some practical considerations. First of all, this is a useless method as such, because you cannot minimize a function on a ball in general. This would need to be a very simple function for you to be able to do that. However, we can approximate f. So instead of applying this Broximal Point Method to f, we apply to a model of f. So maybe we linearize f, or we come up with a quadratic approximation, some other approximation of f, whatever works. So if you linearize f, then what you get is just normalized gradient descent as a method. So Broximal Point Method with the linearized model is just normalized gradient descent. And we know the normalized type gradient type methods actually work very well in deep learning. Okay? So now you can also approximate not f, but the Brox of f. The Brox of f is this optimization problem, this auxiliary optimization problem, minimizing f on the ball. So maybe you don't have to minimize it exactly, but approximately, maybe with few steps of some other subroutine. And maybe you can use both of these approximations. Okay? You can play with one more parameter here, and that is the choice of the norm. So all those results that I showed, they were proved originally for the Euclidean norm, but they hold for any norm. Not all of them. The distance one doesn't, but the function value result does. And it turns out that some special norms are very useful in deep learning. And those of you who are following the Muon literature and shampoo literature, these kinds of papers, you will see that the spectral norm, spectral matrix norm, plays a very important role. So if you do linear minimization over the spectral ball with a stochastic linear approximation and you add the momentum, you get the Muon algorithm. So what I'm claiming here, that the Muon algorithm is nothing else than very special non-Euclidean Broximal Point Method with a very special norm, but an approximate version of it when you apply to stochastic linear approximation of f and you add momentum, Polyak momentum. OK. So there's prior work, as we found out the day we posted this on arXiv by Ian Ta and Aaron Sitford and Eric Harmon and so on. They thought about L infinity balls, LP balls, acceleration under this oracle, and all kinds of other things. All beautiful works, and I would recommend everybody to look at these papers too. All right, so I'll stop here for a moment in case there's any questions. Yes?
Can I ask how stochastic gradient affected the performance?
Yeah, so then none of that theory applies, because that theory is the pure theory of no approximation whatsoever. As soon as you approximate the function, even with linear approximation, let alone stochastic linear approximation, you already are not able to work with any radius. The pure theory says the radius can be arbitrarily large. The reason for that is the approximation is going to deteriorate the further you go from the center of the ball. So you have to limit the size of the ball in order for the approximation to be meaningful for the theory. And this is why we need upper bounds on step sizes in gradient type methods. That's one way how you can think of this. Probably that's the easiest way of thinking why we need step sizes, upper bounds on step sizes in gradient type methods. Gradient method is basically trust region method, okay, with ball trust region and linear approximation of the function. And so once stochasticity enters the picture, the approximation is not only inaccurate because it's linear, but it's also stochastic, so it's noisy. And then the ball would need to be even smaller. But you can compute the approximation faster, right? So there's this trade-off, and so on and so forth. So in fact, in part 3 is where I'm going to be addressing these kinds of questions. Yeah. Yeah?
In the diagram you have your
Yeah?
sinusoidal type thing.
This diagram?
Before that, this one. So this function here looks like an additive combination of two functions, like
Right.
a convex one and a
That's right.
periodic one. So I guess you can consider this like a weakly convex function already.
Yeah, so here, for instance, you can work with quasi-convex or quasi-convex. So all kinds of weaker convexity or limited convexity assumptions or generalizations of convexity would be implying this Broximal aligned condition. And under that, you will get convergence to the global optimum. However, in these ones, you can't really have local minima which are not global minima, so that's difficult for them. But here in this picture, that's possible, right? In this picture.
Yeah, because I think this is a pretty well-behaved non-convex.
Yeah.
But arbitrarily non-convex, you might still have some problems.
Even arbitrarily non-convex would fit in, but then the radius would need to be large, right? Because if you have arbitrarily non-convex function, as long as the radius is so large that the initial ball includes the minimizer, this BPM method is going to solve the method in one step. So remember that this oracle is very, very powerful. But if you're going to limit the radius, then you're going to also shrink the class of functions for which you get global convergence. Okay? And here the radius has to be large enough. So if you shrink the radius below this 2 pi, you might not converge to the global minimum. Okay? Okay. So for those how many of you are aware of this Muon algorithm? Okay, so maybe half. Okay. So the Muon algorithm didn't come out of nothing. In fact, there's lots of work which predated, and I'm only going to review some of it, not all of it. So please, if you worked on this and I didn't mention your work, just let me know. I'll add that slide later on. This is not completely exhaustive. So there's this paper, Shampoo, by Gupta, Koren, and Yoram Singer, where they did this. Okay, and this is supposed to be some sort of a preconditioned gradient time method where you do preconditioning with you multiply this gradient, which is a matrix, on the right by -1/4 of some other matrix, and on the left by -1/4 of some matrix. And it looks all mysterious, and if you just look at it, you may see, okay, I don't know what's going on. Okay, but it's supposed to be some sort of preconditioned method. And they claim that this method, if you can implement it, if you don't count the cost it takes you to do the iteration, if you just count the number of iterations, you can beat Adagrad and Adam and so on. However, if you count the time, then you don't beat, because this iteration is very expensive. You have to do these matrix operations, and then you lose. So it's a beautiful idea, but it didn't quite work. So this has only 400 citations. I mean, this is a very good number of citations, but clearly it didn't replace Adam, right? Then it would have many more citations. However, they're very close to the right idea. So they just should have done this more efficiently and maybe added momentum, and then you would get Muon algorithm, and then you would outperform Adam. So it's very close to the right algorithm. So then there's this paper, orthogonal stochastic gradient descent with momentum, where they almost got the right algorithm. So this is what they say. They very explicitly say that they take the gradient, they turn it into a matrix, and they replace this by the nearest orthogonal matrix, and they use that instead of the gradient. So they have some strange transformation of the gradient into the nearest orthogonal matrix. So it's very explicitly written here. You have some SVD and I don't know what. And then you also use momentum, because there's some stochasticity here as well. and you get the method. This has even fewer citations. This paper doesn't have any theory. However, this is even closer to the Muon algorithm because all they had to do is to implement this orthogonalization using a fast iterative method. And they should have put the momentum in a different place in the algorithm. And then you would get the Muon algorithm. So finally, Muon from roughly a year ago, or a year and a half ago. So what they've done is they add the momentum to the gradient computation, stochastic gradient computation. And then they take the momentum and they apply 5 steps of Newton-Schultz method for orthogonalization. So this is orthogonalization, but it's inexact orthogonalization. So what this is doing, this is exactly the Broximal Point Method, however applied to a stochastic linear approximation of the function with momentum. That's what this is. And for a very specific norm, which is a spectral norm. So this Newton-Schultz, this is just a way of minimizing a linear approximation of the function over the spectral ball. That's what this orthogonalization gives you. So you can forget about why orthogonalization is just minimizing the linear function over a certain ball. That's all that's going on. So there's no theory in this paper because this is not even a paper, this is just a blog post. But very influential because they could beat other methods, but in walk-log time. So this is already very efficient. And this consistently beats Adam and AdamW and so on and so forth. And these are the 5 steps of Newton-Schultz. I'm not going to go through this. Later on, some other authors, with the last author being Robert Garr, my former student, they came up with an optimal method for orthogonalization, the polar express. So you can just use polar express instead of Newton-Schultz in the algorithm, you get a faster method, and so on and so forth. There's a lot of activity now with these Muon-type algorithms. Then, a little bit later on, a few months after the blog post, some theory, an improved theory, appeared on arXiv. So this is very meaningful theory. Actually, there's one better result than this, but I would recommend everybody to read this. This is by Dmitry Kovalov, also my former PhD student. So then Volkan Cevher and his team, they thought of the Scion algorithm, which is Frank-Wolf with some bells and whistles. As soon as you're thinking of minimizing linear function over some balls, you can think of this as this is reminiscent of Frank-Wolf. So there's a very close relationship between Muon and Frank-Wolf, and they have this Frank-Wolf approach and observe very nice hyperparameter transfer where the step sizes actually don't have to be changed as you scale the model. So this is also a beautiful paper. Then we're getting closer to federated learning because now there are distributed versions of Muon. Okay, so maybe not necessarily federated, but distributed, and so on and so forth. So now I'm going to part 3. Before I go there, I ask how much time I have because I don't know.
Maybe like 10 minutes?
Okay.
Yeah, we started a little late.
Okay.
My bad.
So if you have any questions about this second part, yes?
So I've heard that Muon does not work if you actually do the orthogonalization, like the full orthogonalization.
Yeah.
Like somehow it's very important that you're doing just a couple iterations of Newton-Schultz and you're getting some kind of weird intermediate. How does that fit in with kind of the theoretical understanding of these things?
I do not know that it doesn't work. It just gets slower, maybe. But it works. It still will converge. It's a valid algorithm. But the sweet spot is doing it approximately. Why? We don't quite know. We don't even know. I mean, we don't know any mathematical properties or precise mathematical properties of these models we apply this to. So we don't know whether that's the right thing. But at least it's sufficiently better than AdamW that it gets people excited. Okay. Okay. So at the time of us thinking about Muon, there were only these 2 papers that did any theory that I mentioned by Dmitry Kovalov and these other authors from February. And we're looking at those results and we're thinking, okay, what is missing in those results? And we realized that there's 2 main issues. First issue is that if you look at the theory of these papers, they assume that the linear minimization is done over the entire space of the parameters. But in practice, when you look at the implementation of Muon, this is done layer by layer. Now, there is a construction where you can think of these things being equivalent, but I don't want to go into those details. However, this is still a weakness. So what we wanted to achieve is analysis of the method which, when implemented, beats AdamW. So with the linear minimization oracle, over the balls is done layer by layer, so not globally. Then, when you look at the step sizes, the theoretical step sizes in these algorithms, they are just not useful at all in practice. You have to fine-tune step sizes in a very different way. This is very common in deep learning, so the theory doesn't quite predict what step size you should be using. And we're thinking, okay, what can you do? Can you come up with theory where the step sizes that you get from theory could actually be very close to the best fine-tuned step sizes? And we achieved it in our work. So those are the really two main contributions. So the setup now is, we don't just minimize f, now we minimize expectation of some functions. We have stochastic problem. So we won't be able to compute even the full gradient. We have to compute stochastic gradient. This is not the federated setup yet. This is still single node setup, but at least it's stochastic. And the space is going to be this product of these other spaces. And these will be, you can think of these as p layers of a neural network if you want, or some partitioning of the set of parameters into blocks. So there'll be these matrices, ni, mi on layer I, and we want to minimize this function. So the algorithm is just this. Very simple algorithm. Now that you understand what the Broximal Point Method does, you can recognize that we have a ball of radius tik, but now we have I, and that's because we have multiple balls for each block of these parameters. For each layer, we have a different ball. Okay? And we allow these radii to be different, and we allow these norms to be arbitrary and non-Euclidean. Then we don't apply this to the function itself, but to a linear approximation of the function. Okay, so there's another layer of approximation. And this will be the trace inner product. And that's what we do. This is xi, this is the ith block. This is the momentum. So not the stochastic gradient, but the stochastic gradient corrected with momentum. In the linear approximation, this is the trace inner product. And this is just arbitrary, possibly non-Euclidean ball. So if you want to recover muon as a special case of this, you need to choose this to be the spectral norm for all the layers except for the first and last. There, it's okay to choose infinite norm, let's say. Okay. All right. So that's it. So this is some sort of approximate stochastic version of the Broximal Point Method. So you can only get weaker results than what we got before. We won't be able to get these very powerful results. Because we wanted to get theory which predicts step sizes which actually work in practice, we had to revisit the smoothness assumption. And remember that in Broximal Point Method, we didn't need any smoothness assumption. You have proper closed convex function, could be arbitrarily non-smooth. So we wanted to relax smoothness. And the inspiration was this L0, L1 smoothness assumption used in the literature. However, now we have L0, L1 layer-wise assumption. And it turns out that this is empirically better assumption for the models that we tried than global L0, L1 smoothness assumption, because we could see how these constants vary throughout the layers. And interestingly, these L0 constants are all very, very small, almost zero. And these L1 constants are between 1 and 100. They're also very small. So these are almost zero, and these are very small. So under this assumption, actually then we validate it. We try to estimate this constant, and we have good alignment between the theoretical estimations and the measurements. We obtain this theorem. So the theorem is for this method. First, the deterministic variant with full gradient, and we know that if the number of iterations is at least this, we have solved the problem. Now we have just converges to stationary points. The interesting part is this. This bed term, which depends on epsilon square, depends on the sum of the L0 constants, but those, when we measure, they're all almost zero. So even though you get 1 over epsilon square rate, in fact, this is not the dominant part. So this is acceleration by better modeling of the smoothness of the function. So this is really the dominant part, and here we have maximum of the L1 constants. And those are between 1 and 100. So you see in basically 100 over epsilon iterations, you solve the problem. Now, it turns out you can improve this maximum of the L1 constants to the harmonic mean of those constants at the cost of possibly worsening this dependence here. But this is not necessarily worse. This could be even better than the numerator on the previous slide, but it also could be worse. And then in the stochastic case, of course, we have something worse, and we have dependence on 1/4 of the number of iterations, and this can be improved if you add Pollak momentum to 1/3. So that's it. And this is where I need to end, and I just maybe say 2 sentences about this slide. So now that we have understanding of this Broximal Point Method and Muon, we can think of going distributed and federated, and this is what we've done in this work, where we think of finite sum minimization with arbitrary heterogeneity of the data and the functions. And we think of the model where communication is the bottleneck. So you need to compress communication with a biased compressor, as I was describing a month ago in my tutorial. And then you need to apply error feedback in order to stabilize the method. Otherwise, it may diverge exponentially. And this, you need to show that this is going to work. Before, this was only known to work in the setup of Euclidean geometry. So this is basically extension of error feedback into arbitrary norms. And one can show it works. And in fact, the theory is tight. If you plug in Euclidean norm, you recover the best known theory for error feedback in the Euclidean case. Here, what we do, we compress the gradient itself. So we drop some layers in the gradient computation randomly, and we can prove that this leads to faster convergence in walk-log time. Thank you very much.
Great. Thanks so much, Peter. I think maybe in the interest of time, we'll hold off on questions for now, but please hang out because we have a break after this next speaker.